We've spent a lot of time over the past several lessons talking about quadratic functions and quadratic equations. In this lesson and the next lesson, I want to finish our discussion about quadratic equations by talking about objects known as the conic sections. So to begin, let me share some brief history about the conic sections. There are four basic conic sections: parabolas, which we know quite a lot about already, hyperbolas, circles, and ellipses. They were popularized by a Greek mathematician and astronomer named Apollonius of Perga in his book, which we call Conics. Apollonius lived from about 260 BC to about 190 BC. So these conic sections have been around at least 2,200 years or so in terms of mathematical study. Apollonius was very influential in the study of these graphs. In fact, most believe that it was Apollonius who started using the terms parabola, hyperbola, and ellipse. So why are these objects called conic sections? Well, that's actually a very good question. I'm glad you asked it. The answer is a very visual one. I want you to start imagining the following. Picture a cone, like a pointed ice cream cone with the wide part on the table and the point of the cone sticking up in the air. It's sort of like an upside down cone if you were putting ice cream into it. Now imagine placing another cone on top of this one where the pointed ends are touching one another. So the opening of one cone is pointing down and the opening of the other is pointing up. This is sometimes called a double cone for obvious reasons. Now, next I want you to imagine that we take a very sharp, flat blade and cut through this cone at different angles. Depending on the angle that blade goes through the cone, you'll end up with some sort of cross section. And those cross sections are exactly the conic sections. So we started with a cone, and that's where we get the word conic, and we're going to cut them into cross sections, and that's where we get the word sections, hence the phrase conic sections. So, for example, if the blade goes through one of the cones in a completely horizontal fashion, then the cross section will be a circle, as long as the blade doesn't accidentally go right through the place where the two pointed parts were touching one another. If you go through one of the cones and the blade is horizontal, the cross section will just be a circle. If you change the angle of the blade just slightly and you cut across one of those cones, then you'll stretch that circular cross section into something that looks a bit more oblong, almost football shaped. It's not football shaped, but it is a bit stretched out. And each of those cross sections are called ellipses. A single one is called an ellipse. And I'll talk a lot more about circles and ellipses in the next lesson. Now, if you change the angle of the blade so that it's slightly steeper than the angle of the side of one of the cones, then the cross section will no longer be a closed curve like a circle or an ellipse. And what you get then is something you already know a lot about. That cross section, where the angle of the cut is quite steep, but not vertical, is called a parabola. And we know lots about parabolas. And lastly, if you take the blade and turn it completely vertical before it goes through the cones, well, in that case, you actually cut through both parts of the double cone, and what you get looks a little like two parabolas, one sitting above the other. Well, they're not exactly parabolas, but the shape that you get, which is a U on top and a sort of upside down U on the bottom, is called a hyperbola. And in this lesson, we're going to talk about parabolas and these hyperbolas. Now, I really want to emphasize one thing before we move on. These hyperbolas look a bit like two parabolas, one glued above the other. It turns out that the hyperbolas aren't really parabolas at all. They are sort of U-shaped, but they're very different. And by the end of this lesson, I'll explain to you the difference between the U-shapes you get with a parabola and the U-shapes you get with a hyperbola. Now, another question you might ask is, well, why are you telling us about these now? What's so important about them? Well, the answer to why I want to tell you about them now is that because all of the equations that have these conic sections as their graphs are quadratic equations. And you and I have been studying quadratics now for quite a while. We're very comfortable with those. Every one of the equations for a circle, or for an ellipse, or for a parabola, or for a hyperbola has either an x squared in it or a y squared in it, and it might have an x squared and a y squared in it. And so this is the right time to be discussing conic sections because the algebra behind them is very quadratic. Now, let me share one last historical comment with you before we get into the actual algebra today. I have to be honest, when Apollonius and his Greek friends were studying the conic sections, the concept of algebra as we know it and as we're studying it together hadn't even been invented yet. Those early mathematicians, Apollonius and his friends, were only studying the conic sections from a geometry point of view. I'm going to try to give you a bit more about the geometry of these objects in this lesson and in the next lesson. But my focus is really on the algebra. So we'll talk a little bit about the geometry, but I really want to get to the algebra, to the equations that govern these images, that govern these graphs. Okay, let's transition now to some comments about parabolas. This lesson is mostly about parabolas and hyperbolas. I know you've talked a lot about parabolas already. We've worked through a lot of examples, so I won't drag us through too much of that in this lesson. But let me tell you how parabolas are viewed as conic sections, geometrically the way Apollonius would have viewed them. So let me explain that geometry in the following way. I'm going to give you an alternate definition for the parabola, which doesn't say anything about its equation at all, but talks about the geometry of it. So here's that definition. It's sort of a constructive definition. Take a line in the plane, which for us would probably be either horizontal or vertical. It doesn't have to be horizontal or vertical, but for our purposes in this course, we're going to make it either horizontal or vertical. We're going to take that line and we're going to call it the directrix. Next, I'm going to choose a point in the xy plane which is not on this special line called the directrix. And that point is called the focus. So I've got a line in the plane, and away from that line I have another point. The line is called the directrix, and that other point is called the focus. Then the parabola is defined to be the set of all points in the plane that are the same distance from the directrix as they are from the focus. So, for example, if we let the focus of a parabola be the point 0, 1, and we choose the directrix to be the horizontal line, y equals -1, then the graph of the parabola, which is the set of all points that are the same distance from the focus as from that directrix, looks something like this. And if you look at that, that looks a lot like the parabolas we've already seen. It looks a bit flat though, doesn't it? In fact, that parabola has the equation y equals 1/4 x squared. And it's that extra 1/4 out in front, which actually makes the parabola look a little flatter than it would if the equation had been something like y equals x squared. But don't get me wrong, that equation isn't how we started to draw that parabola. Apollonius would have drawn it by first drawing the directrix and drawing that focus and then determining all the points that would have been the same distance from the focus as from the directrix. Similarly, we could have chosen as the focus the point 3, 0, and the directrix could have been the vertical line x equals -3. And then you would end up with a totally different parabola. It would look like the following. And the equation of that graph is x equals 1/12 times y squared. Notice the y squared there, that's the quadratic part of this equation. Notice also that we have x equals y squared as opposed to y equals x squared. And it's that switch in the relationship between x and y which is making this parabola sit sort of on its side, if you will, as opposed to opening upwards. Now, I'm not going to focus much of our attention, pardon the pun there with focus, but I'm not going to focus much of our attention on requiring you to work with the focus and the directrix definition of a parabola. I really only wanted you to see it so that you understood how Apollonius was building them. But let me make one quick point about those equations. It's important that you notice that the equation of a parabola always has one of the variables, but not both of the variables, squared. In other words, you're going to have something like y equals something with x squared, or you're going to have something like x equals something with y squared. So only one of the two variables will be raised to the second power, and the other variable will only be raised to the first power. So that's the first comment I want to make. When you're dealing with equations, and someone just hands you a quadratic equation that has some x's and some y's in it, and some of the things are raised to the first power and some of them in the second, if you want it to be a parabola, the equation then needs to have one of the variables only raised to the first power, and the other variable can be raised to the second power. That's how I know that the graph of such an equation is going to be a parabola. Now, let me make one other comment about the two examples I just showed you. One of those parabolas was sitting, as I like to call it, on its side, and that parabola, you need to notice, is very different from the parabolas that are pointing up and down. And the reason is the parabola that's sitting on its side fails what we call the vertical line test. Remember, the vertical line test says that if you can draw a vertical line between or over a graph and it crosses that graph at least twice, then that graph cannot be the graph of a function. So we actually will not spend a lot of time talking about parabolas which are sitting on their sides because those parabolas are not the graphs of functions. Now, since we've spent a lot of time with parabolas and their equations in past lessons, I want to move away from parabolas today and spend most of our time talking about hyperbolas. So, we've talked about parabolas today. Let's now talk about these hyperbolas. And the first thing I want to do is again walk through Apollonius's definition, which is more of a geometry type definition, for a hyperbola. So bear with me as we walk through this together. Start in the xy plane, if you want to draw a hyperbola, and pick 2 points in the plane. Let's give them names. Let's call them F1 and F2. I'm using the letter F, by the way, because each of those 2 points is called a focus of the hyperbola. In fact, this word focus is going to be used later on, even with things like an ellipse. So we have F1 and F2. Each one is called a focus. The plural of the word focus is foci. So F1 and F2, when you think of them together, are called foci. Now, the hyperbola, which is associated to F1 and F2, is the set of all points in the plane such that the differences of the distances from each of the points on the hyperbola to the 2 foci is a constant amount. Now, that's probably going to be the most complicated definition of a conic section that we're going to see with any of the 4 conic sections. As I said above, I don't want to focus too much of our attention on these geometric definitions. Instead, I'd like to talk about the algebra related to hyperbolas. But again, let me remind you, this idea from Apollonius of the geometry is that you have your 2 foci, and the hyperbola then is the set of all points such that the differences of the distances is a constant. That is going to be in direct contrast to what we talk about in the next lesson with ellipses, where we look at the sums of those distances as opposed to the differences. Now, let's move away from that geometry. I love the geometry, but we're in an algebra class. So let's now look at some equations which govern hyperbolas. There's a lot to do here, and so beyond just the terminology we've already introduced, there's actually a good bit to do with the equations as well. The standard form of a hyperbola's equation always looks like one of two things. It either looks like x squared over a squared minus y squared over b squared equals 1, or y squared over a squared minus x squared over b squared equals 1, where a and b are just non-zero real numbers. So the a and the b are actually going to be numbers. You'll have an x squared and a y squared floating around. Notice that both of them are squared, not just one of them. And from an equation point of view, you always have a subtraction in there if you've written the thing in standard form. Okay? Now, you might be wondering, what's the difference between the two equations you just told me? It sounded like you said the same thing twice. Well, from an equation point of view, the first of the equations I showed you has the x squared in front, and the y squared term is the one being subtracted. The second equation has the y squared in front, and the x squared term is the one being subtracted. But in both cases, there's a minus sign, and both the x and the y are squared. That's how you're going to tell, once you have the equation written in standard form, that you have a hyperbola as the graph. And again, that's very different from a parabola, because the parabola's equation only has one of the variables squared. Now, from a graphical point of view, those equations, the two standard equations for a hyperbola, are actually very different, even though it looks like they're almost identical. Let me show you what I mean about the differences between these two equations by actually showing you an example with two different graphs. So, first of all, let's take the equation x squared x squared divided by 9 minus y squared divided by 4 equals 1. Now, I immediately know that I'm going to have a hyperbola there because I have an x squared term and a y squared term, and I have a minus. Now, the graph of that looks like this. And in contrast, I want to look at the graph of this equation. Y squared divided by 9 minus x squared divided by 4 equals 1. Look at the graph now of that equation and compare it to the graph of the first. Notice that they look very different, and all we did was switch the role of the x squared and the y squared in the equations. Do you see the difference? When the x squared is the term in front and the y squared is being subtracted, the u shapes open up along the x-axis, if I may say it that way. When the y squared is in front, the u shapes then open up along the y-axis. So the graph almost looks like it's getting tilted around one direction or the other, depending on which of the two equations you're dealing with. It's very important that you see that distinction, because in later problems you're going to be handed an equation and you'll be asked to draw the hyperbola. And you'll need to know whether the u shapes open this way or the u shapes open up and down. Okay, what else should we say about these hyperbolas? Because there's more to say. Well, there are a few very important things I want you to notice. First of all, each hyperbola has two vertices. Now remember, the hyperbola is not two parabolas glued together, but we are going to talk about these two very special points called vertices. In the case of the last hyperbola we just saw, the vertices are at 0, 3 and 0, -3. And it's not a coincidence that those 3's are there, given that the denominator of the y squared term in that equation is 9, which is the same as 3 squared. That 3 that shows up in the vertices is exactly coming from the 9, which is 3 squared. Okay? There's one other thing I should point out about each of these hyperbolas. In the case of every hyperbola, you actually have two special lines which serve as asymptotes for the two branches of the hyperbola. What do I mean by this? What are these asymptotes? Well, these two straight lines that I'm calling asymptotes serve like walls or barriers. They act like boundaries to help the two U-shapes know where to go. In the case of the hyperbola x squared divided by 9 minus y squared divided by 4 equals 1, the two asymptotes are given by y equals 2/3 x and y equals negative 2/3 x. Where do those 2 and 3 come from? Well, 9 is 3 squared, that's where the 3 comes from, and the 4 in the other denominator is 2 squared, and that's where the 2 comes from. In the case of the hyperbola y squared over 9 minus x squared over 4 equals 1, the asymptotes are given by y equals 3/2 x and y equals negative 3/2 x. And again, the 2 and the 3 are coming from the 4 and the 9. They're basically the square roots of 4 and 9 respectively. And that's exactly where they come from. Let's look again at the equation x squared over 9 minus y squared over 4 equals 1. Notice a couple things. See how the U-shapes seem to flatten out near the asymptote lines. That flattening of the U-shapes in a hyperbola is extremely different from the way the ends or the legs of a parabola act. The ends of a parabola do not hug or get close to a straight line. So that's a very big difference between parabolas and hyperbolas. Secondly, I want you to notice that these are not the graphs of functions. These hyperbolas are failing the vertical line test, just as I spoke a moment ago about parabolas that are sitting on their sides. No matter which way you draw the branches, whether one is up and the other's down, or whether one is this way and the other one goes in the other direction, you're going to fail the vertical line test. So hyperbolas are never the graphs of functions, but they're still important and they're still useful to understand. So I don't want to ignore them completely, but I did want to point that out. Now, let me make one other comment about these asymptotes very, very quickly. I want you to know that although the asymptotes are very helpful because they serve like natural boundaries, they actually are not part of the hyperbola. So it's very important to note that if you wanted to just draw the hyperbola, you would want to draw the asymptotes in to help you see how to draw the hyperbola. But if all you wanted on the page was the hyperbola, you would actually want to erase the asymptotes because they're just there as guides or as boundaries for the actual graph of the hyperbola. Okay, as we come near the end of our lesson here, I'd like to look at a couple more examples involving hyperbolas just to make sure you've got the information down. There's a lot of terminology here today. There's a lot of differences with the equations. So let's talk a bit about graphing another hyperbola, and I want you to see if you can get a feel for what the equations are telling you when you go to draw the graph. Here's the example I want us to look at. Graph the hyperbola given by the equation y squared over 25 minus x squared over 36 equals 1. Why don't you try that one now? Okay, now let's work it through together. Notice that the equation is already in standard form. I was trying to be friendly by putting it in that form. All we need to do is think through a couple things now about what the information is in the equation. First, will the branches of the hyperbola open along the x-axis or along the y-axis? Well, since the y squared term is the positive term here, it's the one in the front, if you will, we know that the branches will open up along the y-axis, or they'll open up and down, okay? Next, where will the vertices for those two pieces of the hyperbola be? Well, look at the denominator of the y squared term. Since 25 has a square root of 5, we know that the vertices are going to be located on the y-axis at 0, 5 and 0, negative 5. And those 2 points act, if you will, like the launching points for the pieces of the hyperbola. Those are the vertices. Lastly, I also know the equations of the asymptotes. They are at y equals 5 over 6 times x and y equals negative 5 over 6 times x. And the 5 and the 6 come from the square root of 25 and the square root of the 36. 25 and 36 being the denominators in the original equation. So I can start drawing my hyperbola by initially drawing the two asymptotes. I just gave you the equations of those two straight lines. I can plot those two lines. I can plot the two vertices that we just found a moment ago, and then I can draw the two pieces of the hyperbola coming out of those vertices so that the ends of the hyperbola pieces hug or get very, very close to those two asymptotes. They're not going to touch those asymptotes, and they're not going to cross those asymptotes as you get ready to draw the ends, but they're going to get very, very close to them so that the branches of the hyperbola actually get pretty flat looking by the time you've drawn them out at the edges. Now, I'd really like to close with one more example that adds just a little more complication, just so you can see the kinds of things you can run into as you handle these hyperbola drawing problems. So here's the example. Draw the graph of the equation 81x squared minus 9y squared equals 729. Okay, first things first. You should really ask yourself, what in the world will this graph be? I mean, 81x squared minus 9y squared equals 729. What is that? Well, I see an x squared and I see a y squared. That immediately tells me it's not a parabola because the parabola should only have one of the two variables being squared. Okay, not a parabola. I then see the x squared and the y squared with a minus sign between them, and that minus sign is a hint that this is going to be a hyperbola. Fine, but now the problem is that the equation is not in standard form. What in the world do? Do I just quit? Of course not. Let's just do one extra step to get the equation in standard form. And the key here is this. In standard form, the right-hand side should have equals 1. Remember, it's x squared over a squared minus y squared over b squared equals 1. So what I really need to do here, believe it or not, in order to get this equation in standard form, is to divide both sides by 729 so that I end up with a 1 on the right-hand side. Now, let's do a little bit of arithmetic by dividing both sides by 729 and see what the simplification looks like on the equation. Well, the right-hand side is 1. We've already figured that out, but what's the left-hand side? It's going to be 81x squared divided by 729 minus 9y squared divided by 729. And 81 divided by 729 is actually just 1/9. So the first term in the equation is actually x squared divided by 9. And 9 divided by 729 is the same as 1 over 81. So the second term on the left-hand side is going to be y squared over 81. And therefore my equation is actually the following. X squared divided by 9 minus y squared divided by 81 equals 1. And now we have successfully rewritten the original equation into standard form for a hyperbola. So now we're down to wanting to graph the hyperbola given by x squared over 9 minus y squared over 81 equals 1. Why don't you try graphing that for yourself really quickly, and then we'll come together. Well, here's how I'd approach it. Since the x squared term is the positive term, it's the one in the front, if you will, the branches are going to open up along the x-axis now. Also, I should be able to see the vertices pretty quickly here. They're going to be on the x-axis, and they're going to be at the points 3, 0 and negative 3, 0, because the square root of 9 is 3, and the 9 is that denominator under the x squared. Lastly, can I figure out the asymptotes? Because once I know those, I've got the boundaries basically of my hyperbola. And the asymptotes in this case have equations y equals 9 over 3x and y equals negative 9 over 3x. And the 9 and the 3 are coming from the square root of 81, which is 9, and the square root of 9, which is 3. So the asymptotes are actually just at y equals 3x and y equals negative 3x. I can plot those, I can plot the vertices, I can draw the branches of the hyperbola, getting close to those boundary lines, those asymptotes, and I'm done. Now, as we close this lesson, I just want to point out that parabolas and hyperbolas have lots of real-world applications. Whenever you have a chance, stare at the lens of a flashlight or the headlight of a car. You might want to make sure they're off, of course, so you don't blind yourself, but look carefully at the shape of the inside part of that light, where the light rays are getting reflected out. Do you know what general shape is often used here? It's often a parabola. And do you know where they actually put the light bulb, or at least where they try to put the light bulb close in terms of that parabolic shape? It turns out that it's very close to the point that we called the focus earlier in this lesson. That way, the light rays are often aimed very nicely forward, and they give us the brightest light possible. Similarly, many satellite dishes are also built in a parabolic shape with the same kinds of goals to the headlights I just talked about, so that you get the maximum accuracy, if you will, for the beams that are coming in. Hyperbolas are sometimes used in trying to locate objects using radio waves, and some spacecraft are purposely sent on orbits and paths which are actually hyperbolic. So these shapes are extremely important for lots of reasons. I should point out that there's more we could say about parabolas and hyperbolas. In particular, I've not shown you what happens if you move the center of a hyperbola away from the origin. That'll have to wait for another lesson. In fact, it might have to wait for another course. Next time, we're going to talk about the other two types of conic sections. Those are circles and ellipses. I look forward to talking with you then.